Okay, good. Thank you. That's 1 second. Okay. So I think from last lecture, we started the discussion on the just 1 second. The inkjet printing head and the printability of the inks, right? So we talked about there are two types of inkjet printing head. One is thermal based, another one is piezo based, right? So basically, the thermal one is like you are boiling water, and there will be bubble produced, and due to the heat applied here, and this bubble will push a droplet onto the. Push this droplet come out from this nozzle and drop onto this substrate. So that's how the thermal inject printing head work. And also for the piezoelectric ones, so this kind of piezoelectric transducers will deflect if there are certain voltage apply here. And this deflection will push, again, droplet out of this this nozzle. So either of this still rely on the how you control this voltage, and such that a certain droplet will be formed to complete this jetting process. And then we think about the droplet, right? We have, if there are very elongated droplet, and if their surface tension of the material, liquid material, is very low, that's what you have, an elongated droplet. So you can just simply consider the surface tension as a indicator of how easy the droplet will form a sphere shape. If the surface tension is low, it's harder to form a sphere shape for the droplet. If a high surface tension, if you look at this example, it shows a perfect spherical shape of the droplet, right? Also, the how fast the moving platen will be another effect to affect this printing. And usually, if you have a fixed speed of the moving platform, at the same time, you are using a liquid material with low surface tension, it turns out you will have this kind of strike on the platform. But that's not what we want, because you have less control on the accuracy of the printing. Probably what you have on the platform, the patterns of the droplet on the platform, is not controllable. In that sense, it's really hard to control the printing accuracy. And also that is what is needed to be avoided during this process. So we have little specifications. As you can see here, these printing heads are pretty expensive. I mean, even for the cheapest one is like $750, right? That's pretty expensive. And also, in that sense, you want to keep your printing head well, even it's not in use. For example, you want to make your printing head a vacuum, such that the liquid oozing will be prevented. Also, you want to always put the cap on the printing head when it's not in use. That is used to prevent the printing head from drying out, which will make your whole printing head unusable, and you have to pay a very expensive price to have a new one replaced, which is not desirable. The droplet velocity is controlled by the voltage, and if the velocity is too fast, if the droplet drop onto the platform too fast, that will cause a splashing, and again that will make the printing patterns not controllable, and which is again not desirable. So the droplet volumes need to be accurate, such that the 3D part could be printed accurately, because each of the droplet will be accumulated together to have the whole 3D shape. So if you have no accurate control on each of the droplet, that means you have no accurate control on the whole 3D parts volume, which is again not desirable. So there are some other concepts like resolution and the droplet and the drop spacing. So the resolution basically describes the dot per inch, right? So this concept is from the graphical image resolution. So basically in the distance of 1 inch, right? That's if that's the 1 inch, right? How many dots you will have. So that is the so-called resolution. So basically, you can compute it using you can either have the resolution and compute the spacing, or you have the spacing, then you could compute the resolution. But how? For example, you have this numbers, right? Resolution numbers. I mean, from its definition, you know, okay, this is 1 inch, and you have that much of points. In this case, 50, and in this case, that's 100, 200, and so on and so forth. That means, well, you have that much dots in between of these two. That is 1 inch distance. Then what is the distance between each of these dots, which is the spacing between each of the dots? Then use the 1 inch over the number of points. In this case, it's 50, or you could substitute different numbers based on the resolution. But you want to change the unit, right? That's the inch. And it turns out you want to have your spacing in the microns. So what you want to do is do a little unit conversion. So 1 inch is 2.55 centimeter, right? That will be let me think. That will be, that's centimeter, right? The millimeter is 25.4. 25.4 millimeter, and okay, probably we will have a 10 powered by 4. 10 powered by 4. That's, oh, I think I messed it up. So let me rewrite this. Okay, make it more clear. So that's by 4, and that's macrons, right? And this is the number of the points. So by compute this, you will have the final result, which is this number. I think it should be fine. Yeah, I think that's fine. So similarly, if there are more points per inch, then substitute here and have the result coming out. That's that's what, given the resolution, you compute the spacing between each of the dots, right? So how to do it in opposite way? That is, with the spacing, compute the resolution. Same thing. Use this formula, but again, you want to do a little unit conversion from the microns to inches. So I think that will be the most important points you want to be aware of. Other than that, that's simply just a little multiplication, right? So another thing is the ink volumes and droplet size, right? So we can simplify this problem by considering the droplet shape to be a sphere, perfect sphere, which may not be true in the real cases, but for the simplicity of the computation, we can do it. And also, we want to make sure the the surface tension to be appropriate, such that this assumption will stand in most of the cases. But anyway, let's assume the droplet shape is pretty much a sphere. Then we have this equation for the volumes of the sphere, where R is the radius. So in case we have already known the droplet volume, which is 30 picoliters, and we can substitute the volume here, and we can find out what is the radius. And the diameter is twice of the radius. So you multiply it by 2, and turns out you will have your, the diameter calculated. But I think the most important thing, again, is the unit. So you want to do such a unit change, which is essential to make sure this will be correct. Yeah. Any questions so far? Okay. Another thing is this nozzle pitch. So nozzle pitch is the spacing between nozzles on a printing head. I think you have learned what is the geometry of a printing head. It's like a series of nozzles. So on each of the printing head, there will be quite a bit, usually hundreds of these nozzles, and the distance between them is called the nozzle pitch. So how to compute it? Basically, if you know the length of this printing head, and you know the number of these nozzles, you can easily compute the distance between them, right? On the other hand, the droplet spacing is basically, it represents the distance between each of the droplets on the printing platform along this axis. Basically, this is the nozzle moving direction, and with this nozzle moving, with this printing head moving, the droplet will be placed onto this substrate, and there will be a series of droplet, and I just save some time, and the spacing represents, okay, how far these droplets are, right? So I left you a question about the droplet spacing, and we can have a little discussion on it in the lecture, see if you come up with the right answer or not. But as I mentioned, the printing head is moving on the XY direction. So as you can see here, after one pass of motion, there will be certain patterns of these droplets. And you can see there are spaces. There are void space without any material there. So that's why there could be a second pass to fill in these regions, right? Basically, you could even print multiple passes, more than two, to have the material density even higher and higher, right? But how to compute the droplet spacing, right? So first of all, let's look at a typical setup for a droplet spacing question. So basically, if you have a if you know the printing head velocity and also a firing frequency, so let me explain what are the two, right? The printing velocity, if you have a printer, if you have a printing head, something like this, right? All right, it move along this direction, and there will be a velocity to move along this direction. So that is the printing head velocity, right? Does it make sense to you? Okay. And also a firing frequency. So this firing frequency actually represents, well, how many drops will be placed onto the substrate per second. So that gives you this firing frequency. Then how to come up with the spacing? So what you will do is, well, you have V, which is the printing head velocity in millimeter per second, right? And you have the firing frequency. And that is, well, basically within 1 second, how many droplet will be there. And that is if we use we use F to represent this firing frequency, and that is in it has the unit drops per second. So you want to be aware. So if the unit to be hertz, that is drops per second. Now here it's kilohertz. So if that's the case, what are you gonna do? Any idea? Any thoughts on this?
Multiply that number by 1,000.
Exactly. That means, well, you are not having 4.25 drops per second. Instead, you need to consider about this kilo. So that is 4,250 drops per second, right? So be aware of these. Remember, only hertz equivalent is equivalent to drops per second, right? So, okay, let's look at it. So in basically for this equation, you in 1 second, this printing head travels v. So that is what the velocity represents, right? And again, in 1 second, there will be that much drops placed on the platform. So this over this, that gives you the spacing, droplet spacing, drop spacing. So, I mean, that's still quite easy to get to understand. But again, the units. So if we look at the original question, it basically this is asking you to represent the drop spacing using microns. But what we have, we only have millimeter here, right? So then we need to do little conversion of the unit. 1 millimeter actually is 1,000 micron, right? So that will be something like this. Let me draw. Okay, it's incorrect. It should be mu m. All right. So by multiplied 1,000, you converted the millimeter per second to a micron per second. And if we cancel out this, and we cancel out the second, and turns out you will have the droplet spacing in micron per drops, which is what the question is asking you to come up with. So any question about it? Okay. So yeah, I think that's a pretty much you want to come up with for the droplet spacing. Another very interesting aspect is the ink printability. As I mentioned, there are several aspects for the printability of an ink: the viscosity, surface tension, and the inertia, right? So the viscosity, basically, it has a standard definition here, but if we just simply understand it intuitively, you can imagine that is how difficult you want to push the ink through a narrow holes. That's the viscosity. Higher viscosity means the resistance is larger, right? For the surface tension, again, that represents how easy the ink will form a spherical shape. The surface tension is larger, it's easier to form a spherical droplet. Otherwise, it will be a elongated patterns. So that's the surface tension. Another is inertia. So the inertia basically represents the tendency of the object to keep moving in a straight line at a constant velocity. So in this scenario, for the printing head, basically when the droplet come out from this printing head, there will be a velocity, and also there will be an inertia over here. So if the inertia is big, when this droplet hit onto this platform, there will be splashes. There will be splashing, and again, that will make the pattern uncontrollable, which is not desired. So you want to keep the inertia of the droplet appropriate range, such that the pattern of the droplet on the platform will be controlled well for the printing accuracy. So basically, these three give you the idea of the printability, right? But these three governs the ink printability. Then we have little calculation here. So the first one is the Reynolds number. So that is the ratio between the inertial and the viscosity force in a moving fluid. And as you can see here, we have we have this equation to compute the Reynolds number, and a low Reynolds number leads to a laminar flow, and high Reynolds number lead to a more turbulent flow. So in the two cases, if the Reynolds number is low, that means the viscous force dominant. And if the Reynolds number is high, that means the inertial force dominant. So, I mean, you want to keep it in a reasonable range, not too low, not too high. As I mentioned, if the viscosity is too high, it's hard to push the droplet out of the nozzle. And if the inertial is too high, you will have a uncontrollable patterns of the droplet on the platform. So that's what the turbulent describes, right? So the Reynolds number have the two inertia and viscosity forces. And there's another Weber number. It describes the ratio between the inertia and the surface tension, right? This is also a ratio. If you look at the equation, a high Weber number will lead to a droplet splashing and break up on the surface substrate. And the low Weber number lead to a droplet that lead on the substrate and the contact. So again, you want to make this Weber number also a reasonable range. But as you can see here, the Reynolds number and the Weber number, they separately linked the inertia viscosity and the inertia and the surface tension. But as we know, all the three will work together to affect the printability of the ink. Then how to link the two numbers together such that there will be a comprehensive description of the ink printability. So that is what the Onsarge number came up with. So basically, it's the combination of the Reynolds and the Weber number by using this kind of representation. I mean, it's by looking at this, it's really hard to understand. But if we just plot it out, then you will have a better understanding. So this trapezoid-like shape, basically that represents the region where a printable fluid should look like. If any Onsarge number falls in this region, that means it's too viscous. It's hard to push the nozzle out of the, push the droplet out of the nozzle. And again, if you have something Onsarge number less than 0.1, you will have the satellite droplet. Satellite droplets represents it breaks, and there will be again uncontrollable patterns on the substrate. Also, if you have a insufficient energy for the droplet formation, that is your Onsarge number falls into this region. That will give you a really elongated shape instead of a spherical shape. And also anything within this region, again, that will be splashing, right? So when you evaluate the printability of a certain kind of ink, you want to come up with this Onsarge number. And ideally, you want to look at this kind of figure. Basically, the horizontal axis is the Reynolds number, and the vertical one is the Onsor number. And by looking at the two, you will have such a printable region, printable fluid region. And then that will help you to evaluate the printability of the ink, right? So that is the printability of the inks. Let me, okay. Here gives you some Onsor number calculator. Basically, you can simply input these parameters, and turns out it show you, okay, where this, if you have such number as the Onsor number, and with all these given, turns out you will know, okay, if the material with this Onsor number is printable or not. Basically, here shows where it is. It is inside this printable region, and the same case happens also. The with the Onsor number, it is inside the printable regions. So that is how you utilize the Onsor number by looking at such a calculator. I think that's another very interesting aspect is the whether you will form a stable line or not. So if you look at this figure, basically the leftmost show you, okay, these droplets are quite separate with each other. You can see the distinct boundaries between each of the droplets, right? In contrast, if you look at this one, well, you will have such a large region. So how these patterns are formed? Basically, that is the that is because of different spacing of the droplets. So we did little computation about the spacing, right? We know if you change the velocity of the printing head and also the firing frequency, the spacing of this droplet will be changed. So, and here shows you different spacing will give you different patterns of the material. From the left to the right, that means the spacing is smaller and smaller. And it turns out this is too close. For this one, there's no overlap of the droplet. And then you have some overlap of the droplet. And again, for this one, you have more overlap, more and more overlap, and which make this printed material to be a perfect line. But if you have even more overlap, that will form such kind of regions. So you want to tune both the speed, I mean the velocity of the printing head, as well as the firing frequency to control the printed material to form a stable line. Also, there will be other aspects to do this computation, and we come up with a equation like this, right? You have the width of bead, the droplet diameter, droplet spacing, equilibrium contact angle in degrees, and substitute them together, you will have a stable printing setup. So what you could do is, if you could measure the width of bead, and also the droplet diameter could be measured as well, and also this angle is measured, then you could compute this droplet spacing and have a good relation, have a evaluation of the droplet. Also, this droplet spacing could came up with by computing using our previous derived equation. That is, you have the velocity of the printing head, and you have the fire frequency, then you have the droplet spacing, right? So you can do it, you can do the computation in different way and figure out whether this is the will lead to a stable lines or not. All right. So these are pretty much all the important points for the inks and also the setup for the stable printing of a line. Okay, I think let's stop here and we will come back. Let me check at 11:05. All right. Then we discuss some metal printing. Okay, let's resume. Oh yeah, let me change the captionist. Okay, there we go. So what we discussed so far is this inkjet-based printing, utilizing the polymer material. And there's some new advancing in this metal printing area. The uniqueness is it has similar working principle as this kind of inkjet-based printer. And let's look at it. Just 1 second, let me find the I think that's we have. Okay, there we go. Can you still see my screen right now? The slides? Okay. So in this new kind of process, the metal wires is melted into the metal mountain, and that is like the inkjet printing. This molten droplet is placed onto the printing platform, and that will form the 3D shape layer by layer. So that is what this kind of printing process work. Basically, this printing process is developed by Vader Systems, and Vader System has been acquired by Xerox. So we have such a printer in the in our Brinkmann lab, since my colleague Dennis Cormier is collaborating with the Vader System, such that we have their #1 printer, their first ever commercial available printer in the Brinkmann lab installed it. Unfortunately, it's out of use right now. There are some problems, and due to the COVID, it hasn't been fixed. So I assume, I mean, I guess there's no way to demonstrate the printer for you guys, but we can look at some videos, see how it works. So the overall idea is with these electromagnetic coil, a time varying magnetic field is produced, and there's a eddy current induced in the metal, in the molten metal. Basically, the coupling of the magnetic and electric field will result a Lorentz force, and this Lorentz force will eject the droplet from this nozzle onto the printing platform, right? That's how it works. Because there is both the eddy current and also this electromagnetic coil, so there are both electric field and also the magnetic field. So they two work together, that result in the Lorentz force, and that push this molten droplet onto this printing platform. So you can see the similarity of this process versus the inkjet based printing, right? For the inkjet printing, they have the thermal based and also the piezoelectric based printing head. But the overall idea is utilizing certain force to push this droplet onto the printing platform. So in this case, it is the magnetic and the electric field work together to push this out of the nozzle. So since it has similar working principle, actually it shares a lot of common consideration for this printing process and the inkjet based printing. But why we need this? If you ever know about the metal-based printer, you will know the most of the printing process for the metal are still utilizing the metal powder, right? No matter it's a selective laser melting or direct energy deposition, either way, they are utilizing the metal powder. But in this one, there's no need to utilize the powder. Instead, it utilizes the wires, metal wires. So the metal wire has the advantage in the cost. As you can see for the comparison, basically it only costs like 37 per kilogram for the metal wire, for the aluminum wires. But that's not comparable if we're talking about the powders. It's much more expensive because the powder is not just a powder. Basically, you need to make sure the powder particle has a uniformly distributed shape, as well as the size. That requires the processing, which will increase the cost quite a bit. Also, the material for the powder is restricted. Not all the material could be make a appropriate powder for the powder-based printing. So in that sense, the costing is the biggest advantage for this wire-based printing. Also, for the handling of the powder is really troublesome, right? We have studied the selective laser sintering for the plastic powder or the polymer powder. It's already quite challenging. For the metal one is even more difficult. You need to think about the recycling, and also you want to maintain the traceability of the mixed powder. There are 3 to 3 principle for the powder, right? Do you still remember? Basically, you want to combine the powder. You want to generate the combined powder with the new powder, brand new powder, some excess powder collected in the box, and also some unused powder during the previous printing for the selective laser sintering. So that means you have to be very clear what is the powder belongs to, the 3 category. That's really challenging. Also, for the powder, there will be concerns about the safety. You know, it is explosive if you do not handle the powder correctly, right? That's very challenging, and also it's sorry. So it is not good for your health if you do not have any protection to handle the powder. And also how to store those powder will be another challenging mission. I mean, for such kind of storage, you need some special treatment and permission from the safety department. I mean, I don't know whether you are aware of it or not. For any source of dangerous equipment or material, there will be a special department at RIT who will come to your lab and check how you maintain or maintain your equipment resources, also how you store the material, and if it does not satisfy their regulation, well, you cannot do anything. Basically, you have to take care of it and meet their requirement. Otherwise, you cannot use the machine and use the material. So that's very strict because that's for the security, for the safety, right? But for the powder-based process, there is such kind of requirement to utilize them or store them properly. And again, the speed. Basically, there could be two aspects for the speed up of the printing. First thing is the multi-nozzle. So right now you are looking at only one nozzle, right? But if you look at if you recall your memory for the inkjet-based printing, what you have is a, oh, let me think the no. Let me redraw it. So for the printing head, what you have is you have all these nozzles located on the printing head, right? So you have usually hundreds nozzles on a single printing head. So similar thing could be happen for this printing process. That is, you will have multiple nozzles placed on the one single on one printing head, and that will speed up your printing quite a bit. And because there's no powder involved, so the powder loading, cooling, or upload time will be saved as well. So that's also another advantage in terms of speed. So as I mentioned, the powder are usually more expensive, and it is 5 or 10 times more expensive than the same material, but in a wire or bulk form. So in that sense, you can see how much it could be saved if just to switch the powder-based printing to this wire-based. But I think there are also challenges for such kind of printing. As you can, if you look at some following illustrations, you will understand there will be challenging for the accuracy for the printing, and the printed parts are still quite rough in terms of the surface finishing and also the surface accuracy, and that could be the future direction for such a printing process. But let's look at this illustration video here. So basically, that's the printing process I'm talking about. As you can see here, here is a moving platform, and you can see these aluminum wires is fed into the printing platform, and as you can see, well, you have the final 3D shape printed. So what are the parameters for this printing? First of all, the nozzle temperature. Basically, you need to melt the metal wire to the meltants, and also the platen or the platform need to be heat up as well, such that there will be a good adherence of, adhesion of the droplets and the platform. So another thing is the nozzle diameter, right? How big the nozzle is, that will control the feature size of your prints. Firing frequency, tool pass, that is how you move your nozzle, how you move your printing head. There are several aspects, aspects as well. The step over distance per drop, the layer thickness, and so on and so forth. So it's very similar to the inkjet printing. So you can imagine how you control the spacing by tuning the droplet firing frequency and also the velocity of the printing head motion, right? So some of these aspects, for example, if you are using the aluminum wires as the material, then you need to heat it up to 850 Celsius to 900 Celsius. And also you want to heat up your printing platform to 400 Celsius, such that the temperature difference between the material and also the printing platform will be not too much. That will help the adhesion. And roughly the nozzle diameter has 500 micron. That's pretty much governs the smallest feature size of the prints. Again, this firing frequency gives you the how many drops per second will be placed onto the pattern. So as you can see here, this here shows you how this magnetic and electric field work together to push the droplet through this nozzle. Basically, that's a simulation of these fields. So here gives you another simulation of the droplets. As you can see here, there are multiple drops, right? That's actually you don't want to have. These are called satellite drops. Beyond the major one, there are a separate one, which is called the satellite drops. But that's what you want to avoid, right? Let's look at more videos about the printing process. As you can see here, the firing frequency is pretty big. It's almost like a continuous flow of the prints. But if you slow it down, you will see these individual droplets and how they pushed onto these layers and accumulate the whole 3D shape. So there are different droplet and spreading could be achieved by setting up the velocity of the printing head as well as the firing frequency. You can see for some, if we look at this, these droplets are relatively separate. That means the spacing between them are larger, and there will be some void regions between each of the droplets. So if you decrease the spacing, make more and more overlap, you will have all these patterns, more continuous patterns. Similarly, you will have some other shapes, some other setup like this. So what it does is basically, if you can decrease the droplet frequency, and that means the increase the droplet frequency. That means at the same time, for the same time period, there will be more droplet. And in another word, the droplet spacing will be smaller. So that is one parameter you could control, the droplet frequency. And that will lead to a more continuous path, right? On the other hand, another parameter you could control is the droplet separation distance. And in that case, you could change the motion, the velocity of the platform motion as well. And if this distance increase, you will have more separate droplet, and vice versa, right? So these are the parameters you could play with, and the appropriate combination of the two will be the one you want to achieve. So if you look at the effect of the droplet frequency and the spacing, for example, if the spacing is like 0.05 millimeter, and also at the same time, if you change the droplet frequency along this axis and change the spacing along this axis, there will be the different effect. So which one you think is best among all these? Any idea?
I'm thinking that the 67 hertz and the 0.05 milliliter drop spacing
You mean this one, right?
looks pretty good.
Yeah, I mean, I agree with you. So again, you want to have a stable straight line. That's what you want to have. In that sense, such kind of experiment really make a lot of sense, right? You tune with the, as I mentioned, you could tune with the droplet frequency and also the spacing. But what you really want to have is the best, right? By setting up different values of the two. And such kind of experiment will give you, okay, pretty much this is what you want. 0.05 millimeter spacing and also 67 hertz for the frequency. So this is how you design an experiment. First of all, limit the number of the parameters, right? Now we have two, which is perfect. And then basically divide the whole domain of the parameter, whole range of the parameter into small segments. I mean, basically you want to do a little sampling for the whole range. And then you have, by combining the two parameter, I mean, the samples of the two parameter, you will have each of the individual points, which are, in this case, which are 2D points. So at each 2D points, you have a specific, in this case, specific spacing and a specific frequency, droplet frequency. And use that set of parameter, you could have a printed trace. And by putting all these traces together, you will easily figure out which one is the best. And that is how they came up with this figure. So, I mean, that's what the graduate student work on, this kind of project, to design your experiment, to decide your parameter, and to figure out how the parameter will affect the result, right? So basically, there are also other experiments. As you can see here, for the there will be a combination of the built platen temperature and jet temperature, as well as the jetting frequency. And again, by tuning them, by combine them together, as you can see for this block, you have 3 different frequency. And you could also set up different jetting temperature and also the platform temperature and see how it look like. Same thing, change the temperature, change the build platen temperature. I think these are the same, still the same as these two, but the difference is how you change the build platen temperature. And the same thing happens if you decrease it to the room temperature. That means basically you do not heat up the build platen. So obviously, this one gives you the best result of the prints. If you heat up the, I would say probably this one's even better. But no matter how you want to heat up your build platens, if you print it in the room temperature, the pattern shows a non-desired prints for the 3D object. So that again approves the effectiveness of the build platen temperature to be around half of the jetting temperature, right? So for the jetting, we have little computation. What you usually know is the mass per droplet and the density of the metal, right? That is related to the material. And the jetting frequency, that is what you could control. Basically, you could tune the voltage applied to the electrical magnetic field, and that will affect the jetting frequency. Also, the desired width and height of the printed track, you could set it up, right? These are the known values. Then how could you calculate the printing head velocity? So what you want to do is, well, for this velocity, basically what you want to do is, so this is the volume of the droplet, right? And then you have the firing frequency. That is how many for 1 second, how many droplets you will have. So by multiply the two together, you will have in 1 second how many what's the volume for the material, right? And then you could divide this volume by this cross-section area. So TW times TH is this area, right? So this is the volume per second you want to have, and this is the cross-section of that volume. Then this will give you the length of this volume, right? But that is what happens for 1 second. So basically, it is coincident to how much this printing head will travel in 1 second. So that gives you the velocity. So does it make sense to you? Any question about this? You got it? Okay, good. Yeah. So the trick here is what you could assume is the printed material will be always, okay, let me, I think my drawing is bad, but just to use this one's better. So you can assume the printed patterns is some cuboid shape like this. So in that case, you can convert this printing head velocity to the length of this cuboid. Basically, that is in the unit time, how much the printer head travels will be equivalent to, in this unit time, how much this length will be. So if you understand this trick, there's no any other issues to understand this computation, right? Then what you want to do is, okay, let me compute the total volume of this shape, right? That is what it does here, right? And then for this cuboid, how to compute this length? Then, I mean, you know the volumes, and you know this cross-section area, which is this, and use this total volume and divide it by the surface volume, I mean cross-section volume, then you will have the length of this cuboid, which is the velocity here. That's how we come up with this, right? And okay, then what is the droplet spacing if we have known this velocity? Well, that is, you have known this velocity and you have known this droplet, I mean, firing frequency of the droplet, and just sorry, just it same as what we did for the inject calculation, using this velocity over the firing frequency, then you have the drop spacing. Yeah, and that's it. And there are some discussion for this drop spacing. So there could be some extreme cases like the one shown here. You have 100% overlapping if this red one and this blue one represents two droplets. That means, well, they are 100% overlap to each other. And that means the spacing of the two droplets is 0. This DD is 0. And that gives you the 100% overlapping. Or there could be 0 overlap. That means there's no overlap at all. And in that case, this spacing between the two dots, this is the distance, is equivalent or larger than its diameter, than the droplet's diameter. And and we substitute this here, that gives you what happens if the spacing is when there's no overlapping. Basically, if the spacing is equivalent or larger than its diameter, than droplet's diameter, that means there's no overlap at all. That gives you the 0 overlap of the droplet. Okay, that's the percentage of the overlapping. Yeah. Any question for here? Okay, good. And there will be some thermal control for this process, such that the microstructure will be different. So when a hot droplet land on a substrate which is cooler, which is in cooler temperature than the droplet, so there will be some something happen in the microstructure level. Basically, there will be a rapid solidification at the bottom, right? Because it's cooler. So that solidification will happen faster at the bottom, and slower solidification or cooling at the top. And what it does is there will be a non-uniform grain size. As you can see, basically this shows you what's the difference, right? You can see the grain size for this one is relatively large and this one is smaller, and there's a clean interface between the two. So this kind of macrostructure will lead to a poor material property, and that will essentially affect the usage of this kind of process for many applications, because it's not, I mean, there will be some weak points for the structure, and that could break the whole object in certain extreme cases, right? So that's why this kind of thermal control is important. Basically, you want to do little control to make sure the substrate temperature and also the droplet temperature is not too different, and that will kind of avoid such kind of problems quite a bit. Another thing is this precipitation hardening for the aluminum alloys. So you can, as you can see here, for the alloys, there will be different elements and combined together. And for the 60, 61, and the 70, 75 aluminum alloy, they are considered difficult or impossible to be produced, to be used in the powder-based process. For this kind of process, that is definitely possible. And also this kind of process will make the material even stronger, which is perfect for utilizing this aluminum alloy materials. And currently the printer focuses on the 70-75 aluminum. It has a higher strength and a lighter weight. Also, it is a major material for the aerospace components, structural ones. Also, it is pretty good to the stress corrosion correcting. Again, that is desirable for many applications like the aerospace applications. So let's see some of the result using this 70-75 aluminum as the material. Again, the nozzle diameter 500 micron, 950 Celsius head temperature, and also 450 Celsius platform temperature, and also the firing frequency 430. And also this shows you a deposition rate, which is a volumetric rate of the deposition of the material. Sorry. As you can see here, it gives you the macrostructures of the printed materials. So I think it's pretty good, especially, I mean, except there are some cracking points here, but overall, in general, the macrostructure is good. And then also, this is the only second test at printing this alloy material, which is really encouraging. And again, this kind of material is considered as impossible to be printed using the powder-based, but it is pretty good for this the Melton-based printing process. And if we look at the macro structures of the printed layers, and this arrow shows you the printing direction. there are 4 layers of the in the building height, and so basically this is not a single layer. It shows you 4 layers. But from this image, can you tell any interfaces between layers? I don't think so. There is no visible interfaces between the layers. That is desirable, right? That means the different layers are fused quite good. And that leads to a uniform microstructure, which is, again, a good property. So another comparison to be presented here is a comparison between the results printed using this process, I mean this metal printing process, versus the casting. And here shows you the macrostructure of the two results. And as you can see here, it's quite similar. You cannot really tell the big difference between the two. So which again prove the effectiveness and of this metal printing process, and the possible material property of the printing process is similar to what you have through the casting process, right? That is good. If you look at the elemental segregation, basically this shows you what are the composition of different elements, and also the actual wire utilized for the for the printing. And basically that's the reference for you to understand how the printing happens during the printing during the process. Again, this the hardness testing show you its good properties of the hardness for this printing process. Another advantage for this is it is possible to print without support. As you can see here, you can properly set up the printing, the jetting frequency, and also the moving velocity, such that you could keep on adding material onto the previous printed structures without the support. Right? That's a really nice advantage for printing a structure with which usually requires support. But of course, you want to carefully tune these parameters, and also considering about the geometry of the prints. Here shows you again a printing process for the lattice structures. So which is, I mean, can you see the droplets here? That's really small droplets, so it's almost invisible. And as you can see here, if you change the angle of the droplet of these structures, it still can self-support themselves. That's really nice principles. Here give you some statistics for these prints. For different angles, if you look at this horizontal, I mean vertical axis, it shows you the different angles. First of all, it's 90 degrees, and basically smaller, and smaller, right? But at the same time, okay, this is not a 90 degrees. So I shouldn't use this, but this is 90, around 90, and this is like, I would say 70 or 55, 40, 45. I think this one's 40 or 35 something. But at the same time, you also want to change the droplet spacing to increase the spacing such that it can achieve the similar similar patterns for the prints, and that could self-support them quite well. With the angle decrease, the droplet spacing should be increased such that it can still self-support the structure. So that basically this kind of print suggests a good way to produce this engineered lattice structure. So this kind of lattice structure has less material consumed, but still it maintains high mechanical property or structurality, which is desirable for many applications, especially the aerospace and aeroplane components.
Due to superior manufacturing and ink
I
ejection
think
methods,
there's a, okay, let me try to, I don't think we need a sound. But here show you a multi-nozzle array, which is the one already utilized for the inkjet prints, right? So that is one possibility to speed up this printing, which is, well, you have hundreds of printing nozzle, and you can print, you can eject the metal molten droplets at the same time, and that will increase the frequency, right? That's one thing. Another thing is try to utilize more alloys or even steel. So this will definitely a good expansion, significant expansion. That is, if you could produce this part, the part with this metal material, that will greatly save the printing time as well as the cost. Because, for example, the titanium material, there is method to print it using the powder-based. But the thing is, its powder material is very expensive. I mean, only these, I would say, the defense or aerospace application or parts could afford it. So if we can reduce its cost to 1/5 or 1/10 of its original cost, that means a lot. That will definitely help the adoption of additive metal printing in many other applications, right? So that's pretty much I want to introduce for the metal, this liquid metal printing. And in next class, let's talk about the powder, because we have mentioned the powder-based printing quite a bit. And but how it works, why it requires such a high cost, and what is the advantage and disadvantage of these. That will be a very interesting topic to discuss about. So I think pretty much this is all for today's class. And any questions, since we still have little time here? Yeah, any question, not only the one about the lectures, but also if you want to talk about the a project or homework, that's also fine. Anything? Okay. Yeah. And again, have you? I mean, is there anyone who cannot access the Fusion 360 class? Online class. Okay, seems you all have the access. That's good. just let me know if you have any problems about it. All right. So that's pretty much all for today's class. And thanks for your attention.
Thank you, Professor. Have a good week.
Yeah, you too. You too, Cami. Bye, guys.